Assalamualaikum and good day. I'm Marjan Mohd Daud and today I'll be presenting on Casson fluid convective flow in an accelerated microchannel with thermal radiation using the Caputo fractional derivative. You take derivative every day. Your speed is a derivative. It's the rate of change. It's the first derivative of your position with respect to time. The second is your acceleration, how your speed is changing. And acceleration changes, and to measure that would give the third derivative. We could take derivative as many times as we want, and this is well known in calculus. We'll do it all the time. We apply it to all kinds of functions. But here, I stick in the function and I pull it out before it's ready. For example, I take half derivative, pi derivative, and these are all legitimate mathematical operators called fractional derivative that can be defined as a derivative with arbitrary order, whether real or complex order. Fractional derivatives are so little known and so underexplored in engineering, and finding a new way to use them has turned into my master dissertation. A lot of research has been done to better understand fluid behavior due to different kinds of fluids that are categorized as Newtonian and non-Newtonian fluids. The study of non-Newtonian fluids has gained interest in modern technologies such as in geothermal engineering, geophysical, and petroleum industries. Viscosity of non-Newtonian fluid changes as shears are applied, and examples of non-Newtonian fluid are blood, paint, and toothpaste. As Casson fluid is considered as the most desired fluid among all non-Newtonian fluid, the study will be focusing on flow of Casson fluid. It is one type of fluid which behaves like an elastic solid, and for this kind of fluid, it has a finite yield stress which also has the same properties as blood. Fluid flowing in a microchannel recently attracted attention of researchers since it is used in the development of biomedical devices, chemical processes, and wearable devices. This schematic shows the diverse applications of the microchannel in various domains, from microparticle separation and using physical force fields, and to wearable sensing using physico-electrical phenomena. To better appreciate the impact of microchannel, we can make an analogy with the evolution of the computer. In the 60s, one needed an entire room to run a computer. Since then, every component has been reduced in size and laptop products appeared. Now, a simple smartphone is more powerful than any computer built before. This has reduced prices and is much more user-friendly. This paper is motivated by previous research that has been done. So firstly, much research has explored on nanofluid, where Ahmad and Jan, both of them studied on Maxwell hybrid nanofluid and Brinkman nanofluid. So as we know, whenever there are addition of nanoparticles in a fluid, it will have the effect of the nanoparticles to the result obtained. This is because nanofluid will make it emphasize more on the thermophysical properties of the nanoparticles and the fluid. Next, since not many research has covered on the application of fractional derivative on fluid flow in a microchannel, this paper will do so to fill in the research gap. So Saqib has analyzed the application of Atagana-Belleneau fractional derivative to Casson fluid flow in a static microchannel, whereas Imran investigates the Jeffrey fluid flow over an accelerated plate using Caputo-Fabrizio fractional derivative. So motivated by the discussion of the literature review, this paper will be focusing on the problem of heat transfer in Casson fluid, which is a non-Newtonian fluid, and then the application of Caputo fractional derivative will be used to formulate the governing equations for the Casson fluid flow problem through an accelerated microchannel. The microchannel is made up of two parallel plates at distance d apart, and at time t equals to 0, the condition of the fluid is stationary and the temperature of the plate at y equals to 0 is T0. As T increases, the temperature of the plate at y equal to D is raised from T0 to TW, which enhances the buoyancy force. And then it will accelerate at AT when the position of the plate is at y equals to D. The governing equations of the problem consist of momentum and energy equation as shown in equation 1 and 2 respectively. The equations are subjected to the initial and boundary condition as in equation 3, and the velocity and temperature depends on the space variable y and time t. The thermal radiation in this study is optically free in one space coordinate with y, and it is expressed as in equation 4. Applying Taylor series expansion on t power of 4, it can be simplified into equation 4.1. Hence, by substituting back into the thermal radiation, equation 4, the thermal radiation will form as in equation 4.2. Since only energy equation has the thermal radiation effect, equation 2 is transformed into equation 4.3. The dimensional equations of momentum and energy equation, which are equation 1 and 4.3, are first transformed into dimensionless form using suitable dimensionless variables as in equation 5 to reduce the number of variables and discard the units. And then the momentum and energy equation will transform into equation 6 and 7 respectively. Equation 7 is the dimensionless energy equation, and both of the equations 6 and 7 are subjected to the dimensionless boundary and initial condition as in equation 8. After the non-dimensionalization process, the equations are then converted into time fractional form using Caputo fractional derivative. It is worthwhile to mention that the fractional models are more general and convenient in the description of flow behavior. Furthermore, the fractional model's result is more realistic because the obtained results can be compared to the experimental data for excellent agreement by adjusting the fractional parameter. The solutions are obtained by applying Laplace transform method. Both equation 9 and 10, which are the momentum and energy equation, are then reduced into a set of linear ODE as shown in equation 11 and 12. Choosing an appropriate method to solve the equation, each equation are then solved. Since equation 11 is a non-homogeneous equation, the method of undetermined coefficient is chosen to solve the equation to obtain the velocity equation as in equation 13. Whereas equation 12 is a homogeneous equation, the method of solving homogeneous equation is then used to solve the equation and obtain the temperature equation. The problem is solved using Laplace transform method, and the results are translated into MathCAD software programming to acquire the results in graphical form for embedded flow parameters. Firstly, focusing on the different values of fractional parameter alpha, both profiles shows an increasement since the thickness of the momentum boundary layer is minimum compared to the thermal boundary layer at alpha equal to 1. It is said that the classical velocity is at its maximum velocity distribution, whereas for the temperature profile, the properties of classical Casson fluid has a higher temperature compared to the fractional Casson fluid model affect the result as well. Next is the effect of Pareto number. We can see that the increasement value of PR resulting to the decreasing of fluid velocity and fluid temperature. Next is influence of radiation parameter R on the both profiles. It shows that as R increases, the velocity and temperature also increase. Because of its physical characteristics, the greater the value of R, the stronger the convection effect, which results in an increase in the velocity profile. Based on this figure, Casson fluid parameter beta naught shows a contradict result compared to Grashof number GR. As GR increased, the velocity profiles also increase. Meanwhile, increasing in beta naught has reduced the velocity profile. The value of GR will affect the buoyancy force, hence it will also give an impact to the fluid velocity. Each graph previously is plotted with different values of embedded parameters and variables. Influence of fractional parameter alpha is studied for both temperature and velocity profiles. Both profiles shows increasement with increase in alpha. When alpha is increasing, the thickness of thermal and momentum boundary layers are increases. Hence, as a result, both profiles increase. Next is the influence of Pareto number PR. It shows that the profile decreases as the value of PR increases. PR gives effect to the increasement of viscous force simultaneously with the decreasing thermal force. Thus, the temperature and velocity profiles decrease. The impact of thermal radiation R is discussed in both profiles. Both graphs plotted the same trend, where that in each point with the increase of the thermal radiation parameter, the distribution rise. The physical effect of larger physical thermal radiation gives impact to a larger surface heat flux. Hence, both of temperature and velocity profile of the fluid increase. The influence of beta naught, while other parameters are kept constant, is only studied for velocity profiles. The value of beta naught gives effect to the viscous force and thermal force. So fluid velocity will show a drop reading for a greater value of beta naught. The reason is that the viscous force would be enhanced by a higher value of beta naught as compared to the thermal force, which will resulting in decreasing the velocity of the fluid. And GR also is only applied to velocity profiles. As GR increases, the velocity profiles also increase. The value of GR will give effect to the buoyancy force, hence it will also give an impact to the fluid velocity. Here are the list of the reference that has been used. So that's all from me. Thank you.